We look at more properties of linear transformations. The first one was that if I know the coordinates of a vector, then I can completely determine where that vector is being sent by knowing where I and j get sent. If that vector has three coordinates, it would be where I, j, and k get sent, and so on. So we saw that. The second property, or yes, second property or special, or a special property of linear transformations is that it will map lines onto lines. So if I've got a linear transformation, okay, points are, let's say from R2 to R2. So points are mapped onto points, but let's say I've got a line like this, which has a whole bunch of points. So all these points will get mapped onto the plane by a linear transformation, but it won't be able to be mapped into some funky curve like this. That's not possible with a linear transformation. That's due to the properties that it has to satisfy. So by using the properties, we can actually show that all these points will reappear onto a line. Maybe not the same line, but it will reappear onto a line. So lines are mapped onto lines. And maybe I want to explain why that's the case. Now imagine I've got this line here in R2. So how is it defined? Well, it goes through a point P0, and it's pointing in the direction of some vector. So the vector equation of that line would be xy would be some point P0, maybe with coordinates x0, y0, maybe this, plus a multiple of vector v. Okay. So if you don't mind, maybe I'll replace this by P0 plus some multiple of vector v, where t is that multiple. That multiple, it's any number that I can choose from R. So this generates all these points, right? By varying t, we can generate all the points, right? Because to generate a point, let's say here, I go to P0 and then I move by a multiple of v, and I'm going to be able to reach that point. And I can reach any point on the line like that. Now let's take a look at how these points get transformed. Okay, so I take any point, P0 plus TV on that line, and I'm going to look where it gets sent. Well, using property 1, what does it tell me? If I'm adding two things together, I can break it down into the linear transformation evaluated at each of them, and then add those up. So this is going to be t of P0, and TV is a vector, so P plus t of TV. So I can do that. Next property that I can use is the fact that if I've got a scalar times a vector, the image of that through the linear transformation is that scalar times the image of the vector. So in other words, I can sort of pull out, right? You can pull out the k. So I'm going to do that. I'm going to pull out the t in front here. So that's going to be t of P0. I'm not changing that first term. And the t, I'm pulling it out. So I get P0 plus TV, like that. So, okay, and let's take a look at this. T of P0, that's where P0 is sent, okay? So, let me change back colors. So P0, well, maybe it gets sent, I don't know, maybe here. So think of that as a point right here. This is a point. This is T times, T of V is another vector, right? Because V here, okay, is, okay, I've placed it here, but since it's a vector, I can place it anywhere I want to. So V is actually, its coordinates would be the terminal points of the vector V if it starts at the origin. Okay, so that would be some point, right? V1, V2. Okay, that corresponds to V. If that point or that vector is going to be mapped onto another vector, maybe a vector like this. Okay, now take that vector, translate it here. right? So this is t of v, that's some other vector. Now, if I multiply that vector by some parameter t, then that means I'm allowing myself to move along this line starting at t of p0. So this is a line here passing through t of p0. Okay, let me t of p0 and parallel to the vector tv, right, or pointing in the direction of tv. So that's also a line. So that shows you that all these points are mapped onto other points that are part of a line. So in fact, we could actually say that any transformation, no, okay, I'm not done there. I was going to say something, but I need to do property number 3 first. Forgot. Property number 3. A linear transformation maps the origin onto the origin. So if we're dealing with linear transformation, the origin will stay where it is. So if we're mapping, let's say, from R2 to R2, origin will just stay where it is. If we're mapping from R2 to, we could be from mapping to R2 to R, we're going to map this origin onto this origin here. So the number 0, essentially. If we're mapping from R2 to R3, we're mapping onto this origin onto this origin. Okay, so these two origins are not the same necessarily, but one origin is mapped onto the other origin. How can you prove this? It looks obvious, but it's not, right? It's not the case that t of 0 is always 0. That's just what we're trying to show. So we have to use the two properties in order to show this. So this is a good challenge for you. The two properties are this, right? So I'm allowed to use this, and that's it. That's the only thing I'm allowed to use. Okay, and I'll tell you what, you don't even need the second one. So just using the first one, you're able to show that t of 0 is 0. So try this. This is a good challenge to see if you can prove this. So stop, pause, and come back. So t of the origin. So I take the origin. Okay, I want to show that it's equal to 0. So I'm going to write this is something. I'm going to do something funny, but it's because I want to use the property of linear transformation. I'm going to write the origin as the origin plus itself. That's true. 0 plus 0 is going to be 0. Right? If this is a vector 0, 0, and I add the vector 0, 0, I do get the vector 0, 0. Okay, so that works. Okay. Now, using the property above, right? If I use this, that's going to be t of 0 plus t of 0. Right now, I don't know that t of 0 is equal to 0. This is what I'm trying to show. But look what I have here. I've got t of 0 is equal to this. But that's, hang on, that's twice t of 0, whatever that is. So I'm going to equate this with this. So therefore, maybe t of 0 is going to be 2t of 0. It's an equality, so it's a vector. Like imagine it says if I have v equals to 2v. Well, I can send the v on the other side, right? So subtract t of 0 on both sides. I can do that. 2t of 0, and I subtract t of 0 on both sides. I can do this. This is equivalent. So this side, t of 0 minus t of 0, that's 0. That's the, well, it's actually the origin in the other space. And 2t of 0 minus t of 0, that's t of 0. Right? It's essentially 2 minus 2, twice an object minus that object. Well, it's just that object. So I do get this. Okay. So that's the proof. It's actually a very neat proof. Because it looks obvious, but it's not. Like it's not true that all transformations, right, or all functions. If I have the function, I don't know, f of x, which is x squared plus 1, right? It's not true that f of 0 is equal to 0, right? This is actually false. So this is not something that's automatically obvious. So our linear transformations, they actually map lines onto lines, the origin onto the origin. Putting the two together, it also means that if you've got a line going to the origin, well, first of all, it stays a line and the origin stays where it is. So it's going to be a line, another line going through the origin. So all lines through the origins are mapped onto lines through the origin by linear transformations. We could actually say that any function that does that is going to be a linear transformation. So it's very restrictive to be a linear transformation. Number 4, I'd like to know what linear transformations are like in general. In particular, I'm going to look at transformations from R2 to R2. So linear transformations from R2 to R2 are of the form. They're of what form? Well, first of all, if I'm from R2 to R2, I take a vector in R2, let's say with coordinates x1, x2. So I'm using x1, x2 because I want eventually to replace that by the vector x. Okay. Well, where is that sent? Well, it's sent onto R2, so that means I need to know where, well, this is x1i plus x2j, right? So I need to know where I and j are sent because the image of x will be x1 times the image of I plus x2 times the image of j. Maybe let's imagine that this is vector AC and this is vector BD. Okay, what I have is a linear combination of vectors, and we saw that we can actually write all of this into this neat matrix vector product. ABCD times x1, x2. In other words, I can write this as A, some matrix A, times vector x. So all linear transformations from R2 to R2 will be of the form A times x. Some matrix times the vector x. In fact, all linear transformations, no matter what the spaces are going to be of this form. Okay. So maybe example here, if I have t of x, which is x is a vector, okay, it maps, I don't know, the matrix is 1, 2, 3, minus 1, 0, 1, 3, 4, 1 times x1, x2, x3, okay. That's a linear transformation. This one is from R3 to R3. It takes a vector in R3. That's another vector in R3. Right? Because essentially it's x1 times the first column plus x2 times the second column plus x3 times the third column, and we get vector, and those columns are vector in R3. So overall you get a vector in R3. So T here is from R3 to R3. And we actually see that where I gets mapped is the first column. It's 1, minus 1, 3. Where J gets mapped, that's the second column. It's 2, 0, 4. And where K gets mapped, K would be the vector 0, 0, 1. That's 3, 1, 1. If I have a matrix that's, let's say like this, what happened there? Let's say it's 1, 2, 3, minus 1, 0, 1, just like that. Okay. So this one, it takes a vector in R3, but it spits back the vector in R2. You can look at this because this is an linear combination of those columns, right? And those columns there are in R2. Okay. So that's how I know it's going in R2. There's another maybe easier way. If you look at the dimensions, let's say I go back up yeah, maybe I'll stick with that one. If I look at the dimensions of that matrix, this is a matrix that's 2 by 3. This is a vector that's 3 by 1. The inner dimensions must match so that I can perform the matrix vector product. And the outer dimensions, 2 and 1, that gives me the image or the result of the product. So it's going to be a vector 2 times 1. So a vector 2 times 1, that's in R2. So I know that this guy right here is in R3. And it's mapped onto something in R2. Yeah, you can take a look at these examples too. This is 3 by 3, 3 by 1. The inner dimensions must match. I got this arrow in the way. So this is 3 by 3, 3 by 1. So the inner dimensions, 3 and 3 must match. So the matrix vector multiplication makes sense. And the result is a 3 by 1 vector. So it's a vector in R3. Going back here, this is 2 by 2 times 2 by 1. So the inner dimensions must match. And we're left with a vector that's 2 by 1, so a vector in R2. And we're going to finish by describing two linear transformations. Okay, so first of all, we're going to describe. Describe means we're going to tell what it does. Describe the linear transformation T of x equals ax, where A is the matrix 1, 0, 0, minus 1. Okay, so T operates on what? Well, first of all, you see if it's A times x, right? So A is going to be right 1, 0, 0, minus 1. You see, the matrix vector product is a linear combination of the columns of A. So I need two inputs here, right? A vector with two coordinates, right? To be able to match these coordinates with the columns of A. So I know that T starts in R2. And what's going to be the image? Well, this is 2 by 2. This is 2 by 1. The inner dimensions, of course, match. So it's going to be a 2 by 1 vector, right? So T is actually from R2 to R2. So we're describing something that operates on points in the plane. Okay, and I can actually just figure out what this is going to be here. So by performing the matrix vector multiplication, I do 1 times x1 plus 0 times x2, so we just get x1. 0 times x1 plus minus 1 times x2, that's minus x2. Maybe it's easier just to also look at it from the point of view where the vector has coordinates a, b, and we're gonna get a minus b, like that. So T of AB is a minus b. Let's take a look. So for example, if I'm here, I've got this point AB. It's gonna get sent onto a minus b. A minus b is down there. So this gets sent across like this. If I've got I don't know, let's take a look at 3 minus 1, it gets sent onto 3 minus 1, 1. So it gets sent like this. So we see that if I've got a point here, it's going to be mapped like that, and vice versa, by the way. Okay, so this arrow goes the other way around too. So what transformation does that? If you haven't found it, here's another thing we can look at. We can look at where I and J get sent. I gets sent onto this. So I stays where it is. So and J gets sent here. So J, which is here, gets sent onto 0, negative 1. 0, negative 1 is there. So this goes like that. Okay, it's so we can see that if you're on the x-axis, you stay where you are. But if you're elsewhere, you get moved across the x-axis. So what transformation does that? It's a reflection across the x-axis. It's a reflection. Okay, so next example. I want to do a rotation. So again, it's the same question. So which linear transformations, which linear transformation performs a rotation by theta degrees clockwise. Okay. So first of all, let's convince ourselves that's actually a linear transformation. So if you rotate the origin, it stays there. So the origin is mapped onto the origin. And if I've got a line, imagine rotating that line. Okay, we're going to get something maybe like this after rotation. So lines are mapped onto lines. Okay. So because of these two properties, we're pretty much convinced it's a linear transformation. So it looks like a daunting task, like to figure out where all the points are going to be rotated, right? So it seems we have to think about all the points. But the cool thing about linear transformation is that we don't. We only need to know where I and j get sent. So only 2 points. And that makes the task really, really easy. Okay, so we're going to start where does I get sent. Okay, well, okay, let's do that right now. I think I'm gonna need a bigger graph. Let me erase this, something slightly bigger, like this. So imagine I is here. Okay, as it gets rotated, the length of that vector isn't changing, so maybe it gets rotated like this. So imagine this is theta, and if as it gets rotated, it's not changing length. So these two vectors, they would lie on the unit circle, wouldn't they? Like this. Now, we know that if I have so theta is down here, but if I place it here, I know that on the unit circle, the coordinates of a point on the unit circle where this is theta, the coordinates are cos of theta, sine of theta. So the coordinates of that point, where they're the same as these ones, but we just have to reflect them across the x-axis. So this is cos theta minus sine theta. So we already have half of the answer. So t of x, right, which is we want to write as ax, because that's what we're trying to find. What's the linear transformation? It's just equivalent to finding what that matrix A is. Well, I get sent onto cos of theta minus sine theta. So we're almost there. And let's look at J. Let's look at J, like that. Okay, J is here. Where's that getting sent? Well, as you rotate, we'll go there. So this is theta. This, as it turns out, is 90 degrees minus theta. So this point here, right, that's cos of 90 degrees minus theta, sine 90 degrees minus theta. But hey, hang on. If we mirror that point across the line y equals x, we're going to get this point here. And as we do this, the coordinates x becomes the y and the y becomes the x. In other words, these guys actually match. These two are equal. These two are equal. So although I could write here cos j gets mapped on cos of 90 minus theta, sine of 90 minus theta, I can actually do a little bit better than that, in the sense it's going to look prettier if I cos of 90 minus theta. That's the exact same thing as sine of theta, because these two must match, because they're one is the mirror of the other across the line y equals x. So this is sine theta cos theta. So instead of cos 90 minus theta, I'm going to write sine theta cos theta here. And that's A. That's my matrix A. So this is, here we have got T of I, T of J, and we're kind of done. So this would be x1, x2. Okay. So that's our answer here. T of A is this. And you can check, maybe an example, if theta is 90 degrees, okay, what do we expect here? Let's see what we expect from A. First of all, if I look at T of I, you rotate I by 90 degrees, it's going to be sent on to minus J. So A should be, in this case, the first column should be minus J. If I look at J, well, J gets sent onto I. So this should be I here. So let's see if that works. If I replace theta by 90 degrees, do I get 0, 1, minus 1, 0? You can check. It works. Cos of 90 degrees is 0. Sine of 90 degrees is 1. And then you're going to get the matrix. So this actually verifies that our answer over here is good. Oh, actually, I should mention that in the next video, I'm going to refer to the rotation matrix as matrix B. So maybe you want to write B here instead.